Okay guys, let's continue talking about support vector machines. In this second presentation, I will explain the concept of kernels. We will pose a problem for solving the non-separable case in support vector machines. And I'm going to explain the sequential minimal optimization algorithm, which is the algorithm used to solve the last optimization part of the problem, in which we have some alphas. So first, to talk about kernels, remember when we talk about linear regression, we were using some features, x squared, x cubic, when we were building our polynomial. If we use some function phi of our input variable x, we can write these features x squared, x cubic as a feature mapping function, like it is written here. So we get input variable x, one scalar, and we construct this mapping phi of x that will give us three values written as a vector of three components, x squared, and x cubic. Okay, so by doing this, we are going from an input vector of dimension 1, only one scalar, to an input vector in dimension 3 when we create x squared and x cubic. So we are going to a higher dimension input space. Now, rather than applying support vector machines using the original input attribute x, then we can use this mapping, and we can replace in our algorithm. If you remember, in the last presentation, the previous presentation, there is a function where you compute dot products of the x of the input variables. So if you want to use kernels, all you have to do is to go back to your formula and replace every x that you see by phi of x. So as I said, we simply need to go back to our previous algorithm and replace x everywhere with this mapping function. Since the algorithm can be written entirely in terms of the inner products, remember this notation here, it means the dot product of vector x and z. So this means that we could replace all those inner products, all these dot products, with the dot products of phi of x and phi of z. Now, let's talk specifically about one kernel function. So this K is for kernel. So a kernel function of x and z could be this way, in which we are saying that the higher dimension input vector will be computed by computing the dot product of the phi of x and phi of z. So if we say that everywhere where we previously had x comma z in our algorithm, now we can replace that with this function, with this kernel function, saying k of x and z. And our algorithm would now be learning using the features phi. So this is basically what we do to use the most powerful version of support vector machines. We define some kernel function like this one. This case is a very simple kernel function in which we simply compute the dot product of the resulting mapping phi of vectors x and z. Okay, and then in our formula or equations, instead of writing this in this notation with these brackets here, with these angled brackets, we will write simply some k of x and z. So this means apply the kernel function, and at some point you need to define what kind of kernel function. As you will see, we have many kernel functions, and some of them are like the most popular ones. So something interesting is that often this function can be computed or calculated inexpensively, even when computing the mapping could be very expensive. So this is an advantage of using kernel functions. So you can move your input vectors x to some higher dimension, and even though you are working with vectors in a higher dimension, the computation of the dot product, this one here, is computed very efficiently, as we are going to see. So this is one of the importance of using kernel functions. By the way, we are moving our points, our x points, to a higher dimension in the hope that in this higher dimension it is easier to classify. So by using our algorithm, an efficient way to calculate k, we can get super vector machines to learn in a high dimensional feature space that will be defined by our mapping function phi, but without ever having to explicitly find or represent these vectors. So consider the square kernel function. So we are saying here, let's work with a kernel function that will be computed by the square of the dot product of vectors x and z. So note here that if x is of dimension n, to compute this, the complexity to compute this is a big O of n. So we can compute this in linear time. Because suppose that this x is of size 3, so dimension 3. All we need to do is to compute the dot product. This is going to take you 3 operations. And once you have computed the dot product, you will have a scalar, and then you just need to compute the square of that scalar. Okay, so keep in mind that computing this kernel, the square of dot product, can be computed in time n. Now, what happens if we want to explicitly write this square of the dot product? So we can, instead of writing this, we can write explicitly the dot product of x and z and multiply it by itself. So here we are computing the square of the dot product. We can rearrange these indexes here to get this expression. And finally, we can rewrite it like this, which, as you can see, this is simply the phi of x times the phi of z, where this phi, the mapping feature, or the feature mapping, is expressed like this. Okay. So when we are saying that we want to compute the square of dot product, if we want to express that explicitly, you will get features mappings of this size. And as you can see, this is size n squared. So here we have, in the case of dimension 3, we will have 3 times 3. So we have vectors of size 9. Okay. And this is why we say that computing this kernel, if we want to do it explicitly, we will need time n squared. But since we don't need to compute explicitly, we can simply do it like in the first time, like this. We can simply compute first the dot product, and then once we have the result, we can square that number. So that's why we are saying, in this case, we are, if our points were in dimension 3, so if this n were 3, and we apply this kernel function, we will be working with these points in dimension 9, n squared, but doing computation in linear time, in time n, big O of n. Okay, what happens if we add some constant So we don't compute just the dot product, but we have also here some plus some constant. It's a bit more general way to compute this square expression. So if we developed again explicitly what we are doing here, we get to this feature mapping function, okay, which is, in this case is even in a larger dimension, and we can define it just in general for any exponential here, for any exponent here, and the dimension of this feature space will be the combination of n plus d taking d at a time. Okay, so this is if you want to compute polynomials. This will be a polynomial with degree d. So in the same way we used polynomials for linear regression, here in support vector machines you can run experiments using kernel functions that will represent polynomials, and this is the formula that you can use to see in what dimension you are going to work your feature space. So this corresponds to all the monomials of the form xi1, xi2, so on, up to xik, that are up to order d. And actually, in the exercise where you are going to work with support vector machines, you will have time to run experiments with different d, and you will see if this improves the performance of your algorithm or not. Okay, so as we have said, we can work in higher dimensions, like n to d, and the computational time will remain linear. So this is a big advantage of kernel functions. Intuitively, this is very important. If the vectors resulting from applying this mapping phi of x and phi of z are close together, then we might expect this product to be large. Okay, and conversely, if phi of x and phi of z are far apart, then the products will be small. Okay, so the kernel function intuitively is telling you how similar two vectors are, or how close they are from each other. If you compute the dot product and you have a large number, that means that these vectors are close. If the dot product gives you a small number, that means that these two vectors are far apart. So we can think of k, of the kernel, as some measurement of how similar are phi of x and phi of z, or how similar the input vector x and z are. Another kernel besides the polynomial kernel is one of the most common used. The next one is the Gaussian kernel. In the Gaussian kernel, we'll define the k function as the exponential to this power here, which will be x minus z. Then we compute the norm of the resulting vector here. We square that and we divide it by 2 times some sigma squared. This sigma is a constant that will be used to define. Let me go to this plot here. For example, this is the plot for some Gaussian function that is centered around x, 0, and it has some width sigma 0.2. So if you increase sigma, you will have a more a Gaussian with a larger width. If you reduce sigma, you will get a Gaussian more narrower than 0.2, and this here. So you can adjust these parameters of your Gaussian. So here you can analyze what happened with this kernel when you consider it to be a measurement of similarity. So for example, here we're considering that X will have the largest evaluation, which in this case is 1. If you consider, for example, some Z that is in 5, the evaluation in this Gaussian will be something around 0.18, 0.17 maybe. And if you compute for another point, which is here in 10, this value will be very close to 0. So as you can see, as you go away from the point that is in the center of the Gaussian, the evaluation is going to be smaller. So as you go far away from X, the similarity will be less. And as you get closer and closer to the X, the measurement of similarity will increase, being the maximum when the point is exactly the same, as in this case X equals 0. In a simple case with X and Z in the set of real numbers, we have this as the kernel function. Now let's analyze what is the dimension of this feature space that we are creating when we use a Gaussian kernel. So first, let's get rid of the sigma, because sigma is just a scalar. It allows just to scale the function, scale up or scale down. So first, let's focus only on this expression here. Okay, and consider for this development, we are going to consider that X and Z are just scalars, not vectors. Okay, so we have X minus Z, and this is squared, and then multiply by minus 1. So if we develop this square, we will get X squared minus 2 times X times Z plus Z squared. Okay, so we have this, and this. And well, after you have multiply this square here, you will get 3 terms, but applying the properties of the exponential, we can simply write it as products of the exponential applied to each of the terms. And the important point here is that if we want to compute this expression here, the exponential of 2 times xz, where here x and z are simply variables, scalar variables, you can approximate this by summing from k equals 0 to infinity this expression here, where you have 2 to the k, x to the k, and z to the k divided by the factorial of k. And because we can write it like this, then we can say that this Gaussian kernel sends our input vector to a higher dimension, which in this case happens to be an infinite dimension. So the Gaussian kernel is a very powerful and robust kernel because of this reason. Okay, so given some function k, how can we tell if it is a valid kernel? So we have seen the polynomial kernel, the Gaussian kernel, and the first one, when we compute only the dot product, is considered a linear kernel. But there are many other kernel functions. You can design kernel functions for specific kinds of data structures. Like, for example, you can define kernel functions for working with trees, or for graphs, or for strings. So you can define different kernels, and people have done that. And the important thing that you need to consider is what we're going to see now. There's a theorem, the Mercer theorem, that tells you what are the conditions necessary and sufficient to design a valid kernel function. So let K be a mapping from vectors of dimension n, combination of pairs of vectors in dimension n, to some real number. Okay. Then for K to be a valid kernel, it is necessary and sufficient that for any one of your m points in your data set, of course, when we have not an infinite number of points, the corresponding kernel matrix is symmetric and positive semi-definite. So these are the two conditions that we need to guarantee in our kernel matrix, where our kernel matrix looks like this. So if you look at the first position here in the matrix, we are saying apply the kernel function to the pair of points x1 and x1. So this is computing the kernel with the same first example in your data set. Then here you apply the kernel function to your first example and your second example. Okay, and you keep going up to applying the kernel function to your first example with your last example, your example m. Okay, so this is the first row of your matrix. The first column will be let's say will be the same row but now converted in a column. So that's why this matrix is symmetric. If you compute the transpose of this matrix, you get exactly the same matrix. So what we're saying here, and this is one of the conditions, is that if you apply the kernel function to x2, x1, the evaluation of this should be exactly the same as if you apply it to x1 and x2. So it is symmetric. It doesn't matter in which order you put here, x1 or x2. So if you construct that for every point in your data set, you should get a symmetric matrix. And the second condition is that this matrix should be positive semi-definite. So it means that you cannot have negative numbers here. Okay, so you can have only positive numbers. And if you design a new kernel function and you verify that this is true, that these two conditions are true, then that kernel is considered to be valid. The idea of kernels has significantly broader applicability than support vector machines. So kernels are very useful and well studied in support vector machines, but you can apply kernels in different learning algorithms. So an algorithm that can be written in terms of only inner products of vectors, where these vectors are attributes of the vectors, attribute vectors, then you can introduce some kernel function and work with kernels. So there are algorithms that are called actually kernel learning algorithms, because the main emphasis on those algorithms is to exploit the benefits of kernel functions.